and we'll do some problems with this. This is really talking about. I mean, the reason why I'm going through enthalpy in this case is because it goes through into the individual bonds in a reaction. So when you're taking, let's say, like a molecule like CH4, and you combine it with O2, it rearranges into CO2 and what else? Water, H2O. But this isn't balanced here. We need to balance this. If you put 2 over here, we put 2 of that should work. So I'll put another. I'm just making sure this equation's balanced. And let's do another one over here. This should work. Yeah. Okay. So if you add two oxygen molecules to one of these methane molecules, you're going to get as a reaction CO2 and 2 waters. And you're going to feel that this is an incredibly exothermic reaction. It gives off a lot of heat. In fact, that's what we use often when we're burning natural gas. That's what we're burning. We're burning the methane. We're using oxygen, combining it with it, giving it a little spark of energy to get it started. Then it gives off a huge amount of energy. So this is a case of an exothermic reaction like crazy. So what I want to talk about right now for enthalpy, change in enthalpy, is that it requires lots of energy to break these bonds. Every single one of these bonds has to be broken and then rearranged to make these new bonds. So if these new bonds are more stable, let's say like the CO2, if that's more stable, like this CO double bond here and that CO double bond there, if all of those bonds over here on this side, like these OH bonds, if all these bonds on this side are more stable than all the bonds on this side, then we will have a more exothermic reaction. So if we just draw what this would look like on a graph, it would look something like this with our energy on this axis and our reaction progress over here. Of course, we need to add just a spark to get this going, so that's a little spark right there, and then it would go down. And it would release energy. Okay? It would release energy because these products are more stable. So how are we actually going to say this in any kind of like numerical way? The way we do this is we look at every single one of these little tiny bonds. So we've got a CH bond right there. It takes a certain amount of energy to break that bond. And the way that we describe that energy is with this delta H. And it's in the units, if you look at your reading, it's in the units of kilojoules per mole. And now that's just an energy of the certain amount of those kinds of bonds. So CH is given off 412 kilojoules per mole. So each one of these, that's a CH bond, this is a CH bond, all of these, that gives off another it requires 412 kilojoules per mole. And this requires another 412 kilojoules per mole. Oh my goodness. And this requires another 412 kilojoules per mole to break this apart. And if we look at the sum of all of these bonds, like a double bond is worth a lot more. So for an OO double bond, it's not actually all that much more. To break this double bond, it takes 496 kilojoules per mole. And over here, this double bond, that requires 496 kilojoules per mole to break this. If we look at all the energies it requires to break these over here, and we do the same thing over here and look at all the bonds on this side, if we compare the two sums, so if we compare all of these bonds summed together, the energy required to break all of them, and all the energy required to break all of these bonds, we would see that it requires a lot of more energy to break all of these bonds over here. Okay, so what does that mean? That means that we can calculate the energy that would be given off if this reaction took place. Because we could see the difference between all of these bonds added together and all of these bonds added together. Okay, so I've started to do this problem right now. I'm going to continue just doing this. I'm going to point out each one of these bonds right here by looking them up in a little table that I give you. But I'm going to use purple to describe all these bonds over on this side. So on this side, we've got this C double bond O bond right here. This is 799 kilojoules per mole. I'm not going to use units anymore. This is 799 as well. Each of these OH bonds are 463. So that's 463. That's 463. This is 463. And that's 463. So now what I'm going to do is I'm going to sum up all of these purples, and I'm going to sum up all of these reds. So if I sum up all of the purples, what I could do is I could say, right, I could say that there are 1, 2, 3, 4 of these on this side. So I could say 4 times 463 equals, so what is 4 times 463? That equals 1852. And this is going to be all in kilojoules per mole. So that's all those. Now here's 2 times 799. 2 times 799. This is 1598 kilojoules per mole. So if you add these together, you're going to get 3,450 kilojoules per mole. So that's how much energy it requires to break all these bonds. Right, so now how much energy does it require to break all of these bonds on this side, the red? So let's use the red. So if I use the same kind of notation, so if I say, okay, 4 times 412, I did 4 because there's 4 of these CH bonds, plus, and there's 2 of these OO bonds, 2 times 496. Put all these together. Well, first I'll do this. 4 times 412. Oops. 1648. And this is 2 times 496. This is 992. You add these together. Oops. 2 plus 1648. You're going to get 2,640. So it's pretty obvious here. These guys require less energy to break apart than these guys over here. So if we want to see how much energy would be given off if we go from here, this state, because we get the same amount of atoms, really, to this state, what you'd have to do is you'd have to subtract these, because it's the amount of energy required to break all those bonds, and these, this is all the energy required to break these bonds. You see what the difference is. So normally, I have to say, normally what happens is you find the delta H of the molecules and not the individual bonds here, but that's what we've been doing. We found the individual bonds here, and you find out what those delta H's or the change in enthalpy is for these over here, and they're given in the opposite kind of notation. They're given in negatives if it's in terms of how much energy is released once they're broken into their little constituents. But for us, we're seeing how much energy is required to put into them to break them apart. So that's why we're doing this a little bit sort of strangely. We're taking the reactants minus the products. Typically, you take the products minus the reactants. But for this small section of chemistry for Dwight Online, we are just doing reactants minus the products. So we're going to take 2,640, subtract that, and we're going to subtract from that 300, I'll use the same colors here just to be consistent, 3,450. And we're going to get 3,450. And we're going to get negative 810 kilojoules per mole. So that means that these products are more stable, and you can actually quantify that. You can say it's more stable because it gives off this much energy per mole, which is just an amount of molecules. So we can say, right, if this right here, this reaction proceeds and it gives off this much energy, that means if it's giving off energy, it's exothermic. But then you can say, well, by how much is it exothermic? By this much. It's negative 810 kilojoules per mole is given off when you change this stuff into that stuff. And I think that's pretty cool to be able to quantify this on this kind of bond by bond basis here. So that's a little walkthrough of how you sum together all the different bonds on the product side. So this is the product side. And on the other side, we've got the reactants in red. And you figure out, right, if these take less energy to break apart, well, then that means that they're not stable to begin with, right? As stable as the products, which are more stable, it takes more energy to rip them apart. So if we want to see the difference, that what would happen if we would take these reactants and then change them into products, we want to see how much energy would be released. Well, what we can do is we can take the reactants minus the products. When you add up all of those bonds, their change in enthalpy, which is this delta H value. And you've got those values as standard values in a little chart that's given to you in the reading. And you can use that standard value chart, and will be given to you on every quiz and every test that you'll take in this class. Okay, so I hope that made a little bit of sense. And we might walk through this again in person, but I think this is kind of a nice little overview of how to do these problems. So try these problems in your workbook and the extra problems that are on a worksheet. Good luck.